Now finally we're going to talk about indicators and how they work. So an indicator is what we use to find the equivalence point or the end point for a titration. So the way they work is an indicator is actually a weak acid or weak base itself. And so it's one color on one side of the equilibrium, and it's a different color on the other side of the equilibrium. So we use Le Chatelier's principle to shift it one way or the other. So example, here's an indicator that is also a weak acid, and so on this side it's going to be the protons attached to whatever the indicator is. On this side of equilibrium we have the protons separated from the indicator, and so when they're together it's one color, when they're separated it's a different color. So in highly acidic solutions, which are ones that have lots of H pluses, that means we're adding H pluses, and so that's going to shift equilibrium away from the product side and back towards the reactants, which means it's going to turn red. If, however, we were in a basic solution which produces hydroxides, those hydroxides are going to react with those H pluses, therefore eliminating those H pluses, so we're removing something from the equilibrium system. If we remove that, that's a stress, and so that means the equilibrium is going to shift over to this side to produce more H pluses to fill in that void. When it does that, it's also going to produce this color, and so that's going to cause it to shift away from red to purple in the case of this picture. So when a scientist is selecting an indicator, they want to pick one that has a color change at a pH that is as close to possible as the pH of the equivalence point. And so you want the color to change at the equivalence point for your particular titration. And remember, that's that jump where we spike up from basic to acidic or acidic to basic. And so you want to get a color change that happens during that spike. And so then the goal would be to have the concentration of the proton attached and proton unattached equal to each other, and so that's the point where they're going to jump from one color to the other. And so at that point we would know that ratio would be 1, which means the pH would equal the pKa. Therefore, when we choose an indicator, we want to pick one where the pKa of the indicator is close as possible to the pH of the equivalence point for our titration. So the pKa for different indicators are usually given to you, and so they're constants. Here's some examples of some different acid-base indicators and their pKa's. And so then when we're selecting an indicator, if we would look at the system that we're doing, so if it's acetic acid with sodium hydroxide, we would figure out what the pH is at the equivalence point for that particular titration, and we'd find one that has a pKa close to that pH. And so acetic acid, sodium hydroxide, that's going to have an equivalence point that is greater than 7 because it's going to be slightly basic at the equivalence point, which means we'd probably use phenolphthalein, Algerian yellow, higher pH. We would know it would be just slightly above 7, so my guess is it would be about phenolphthalein that you would use. For a strong acid, strong base like sodium hydroxide, hydrochloric acid, we know that the pH would be 7 at the equivalence point, and so we'd use something like bromethymol blue that has a pKa of 7. So we can see right here bromethymol blue covered over on a titration curve for a strong acid, strong base. So we see right here when the pH is below 7 it's yellow, when the pH is above 7 it's blue. And so what we would see here is as we are adding the sodium hydroxide to the acid, it's going to be yellow. And then once it hits this point right here and jumps up, it's going to turn blue. And so what that's going to indicate for us is that we have crossed that equivalence point. And so it's going to tell the scientist, now's the point to stop and do your calculations. And here's acetic acid with sodium hydroxide. We see that the color change is up here around the pH of 9. And so with that titration of acetic acid and sodium hydroxide, we have that buffer region, and then the jump up, and then the steady increase. And we see that that jump right there, equivalence point, is about right where the equivalence point or the change point is for phenolphthalein. And so what we would see here is a clear solution that would turn to pink once it hits that point right there and jumps up to the basic region.